Alright guys, let's see how we can solve another question from the second chapter of Mechanics of Materials by Johnston. And in this question, we have a 4mm diameter cable BC that is made of steel, and we know it has an elastic modulus of 200 gigapascal. We know the maximum stress in the cable must not exceed 190 megapascal, and that the elongation for the cable must not exceed 6mm, and we need to find the maximum load P that can be applied as shown. So before we start everything, we need to figure out what's the force in the cable BC. And for that, we're going to draw the free body diagram for the rod AB. And so we're going to have the tension in the cable FBC. We have the force P in here. And since we have a pin at point A, we're going to consider two components, one horizontal and one vertical. We can just show our X and Y in here. And since we are in equilibrium, we're going to use our equilibrium equations. Since we are interested in FBC, if we just do the moment about point A counterclockwise positive as always, should be able to find the relationship between FBC and P. So if we try to resolve FBC into two components, one X and one Y, we can see the Y component is going to pass through A, so it won't make any moment. So we're going to have only, actually, if we want to show this properly, this should be actually in the middle, and this will be FBC. So the Y component is going to pass through point A, so it won't make any moment. But for finding the X component of FBC, we would need to figure out maybe this angle here, alpha, and we have a right triangle in here, which we have this side 4 meter, the other one would be 3.5 plus 2.5, which is going to be 6. And based on the Pythagorean theorem, this will be 6 squared plus 4 squared, or the square root of 6 squared plus 4 squared, which is going to be around 7.211. So for finding the X component of FBC, we're going to have FBC sine of alpha, which would be basically opposite over the hypotenuse. So 4 over 7.211 FBC. So that would be the force. Position vector would be the distance from B to A, which is going to be 6. So this distance. And we're going to have a negative sign because the moment of that force about A is going to be clockwise, so negative. And we're going to have the moment of P, which is counterclockwise, so plus P times the distance from P to A, which is 3.5. This will be equal to 0 since we are in equilibrium. And here our P would be basically 4 times 6 divided by 7.211 times 3.5 FBC. So let's just calculate this. So 24 divided by 7.211 times 3.5. So our P would be 0.9509 FBC. So now we have two conditions for the cable. The first condition is that the maximum stress must not exceed 190. So we're going to go based on this stress in the cable. So this has to be less than 190 megapascal. So since the question is asking for the maximum load, we're going to go with the maximum of the stress. So this will be, we know it's the force over the area. The area is the area of the cable, or the cross section in the cable. So if you just do a cross section in here, we're going to have a diameter of 4 millimeters, so the area would be pi divided by 4 d squared, so pi divided by 4 times 4 millimeter. We're going to divide by 1000 to get it in meter, and this is going to give us the area. So FBC in here would be basically A times the sigma, so 190 times 10 to the 6 Pascal times the area, pi over 4 times 0.004 squared. Let's calculate this. It's pi times 16 divided by 4. That's going to be 2387.6 Newton, or 2.3876 kilonewton. So that's based on the allowable stress in the cable, but we have to watch for something else too, and that would be the elongation in that cable, which we know must not exceed 6 millimeters. So basically we have the deformation 6 millimeter in here, And we have our formula for the elongation FBC over the length of BC divided by A times elastic modulus. And we know this will be equal to 6 times 10 to the minus 3 meter, or the 6 millimeters. So FBC in here would be the area, which is the same thing, pi divided by 4 times the area. So we're going to have the area times the deformation, 10 to the minus 3, times the elastic modulus, which we had in the first line of the question, 200 gigapascal. So times 200, 10 to the 9, that's going to give us Pascal, and we're going to divide this by the length in BC, which was the hypotenuse that we found in here, so 7.211, and that's going to give us another force in here. Let's calculate that. So I'm going to take the 4 in the denominator, and here we're going to have 7.211, and in the numerator we have pi times 0.004 squared times 6 times 200. I'm just going to cancel those two, 10 to the 6. And this is going to give us 2.091 kilonewton, or 2091 newtons. And now we have two values for the force. One of them is 2.38 and the other one is 2.091. So here we have to go with the smaller value, because if we go with the bigger one, this is going to make longer elongation in the second one. So if we pick the first force, obviously we're going to pass this elongation and system and the cable is going to fail. So that's why we have to pick this one, and keep in mind that the question is asking for the P. So we figured that P would be 0.9509 FBC, which is 2.091. And let's see what we get, times 0.9509. So the force would be 1988.5 Newton, or 1.9885 kilonewton, and this is going to be the maximum P that we can have for this question. Hope everything was clear. Let me know if you guys have any questions, and you guys take care. I'll see you in the next video. Have a good one.